Now we shall see about two-dimensional arrays. Coming to this one-dimensional array, there is nothing much interesting about. I mean, just knowing that what is the address of a particular element, where it is located in the memory. Apart from that, there is nothing much thing about to worry. But coming to this two-dimensional array, the main interesting thing is that how you will take that entire matrix into the memory, because your memory is for sure, conceptually we are seeing that 2D array as a matrix, but the way it is mapped in the memory is somewhat different. Okay, now let me suppose take an array of 3 cross 4 size, where 3 is the number of rows and 4 is the number of columns. So let me take an array, suppose 0 1 2 0 1 2 3. So the elements will be 0 0 0 1 0 2 0 3, which is pretty obvious. We all know that how matrix is formed of a two-dimensional array: 1 2 1 3 2 0 2 1 2 2 2 3. Okay, now as I told you that the array can have index starting from 0 as well as from 1. So again we'll have another matrix for this same 3 cross 4 array, which will be starting from index 1. So let me make it. So it is 1 2 3 1 2 3 4. It is 1 1 1 2 1 3 1 4 2 1 2 2 2 3 2 4 3 1 3 2 3 3 3 4. Now conceptually or theoretically we know that our array will look like this, that it will be a two-dimensional matrix. But suppose if you want to take this entire array and just put it into the memory and just don't do anything and just take it and put it. So what drawback we will have is, suppose we have a memory like this. Suppose I'm just drawing it roughly. Suppose we have a memory like this. So if I take this row and put it here, 0 0 0 1 0 2 0 3, maybe some other this is so on and so forth, it is continuous, and after that we take the next row and put it in the memory. Suppose 1 0 1 1 1 2 1 3, and then 2 0 2 1 2 2 and 2 3. Now the main drawback is that this is entirely contradicting the main feature of array, that is contiguous. See here 0 0 0 1 0 2 0 3 is contiguous, then we are having some other elements, so on, and then again we are having 1 0 1 1 1 2 1 3. So there is no point of using array anyways. If you are losing the characteristic or the feature of contiguity, then why are you using this array? Then we can directly assign each and every variable to this. Otherwise, if we want to directly map it into here, then we will have to use some pointers from here to here, and then some linked list, then some arrays of pointers. That will be much more complex. So our main intention here is how we can map this entire two-dimensional array into the memory. So the answer is that the entire two-dimensional array is mapped as one-dimensional array inside our memory. So how it is done, now we shall see that. There are basically two ways how we can do it. One is row major order and the other one is column major order. Row major order. So we shall see how row major order works first. Suppose row major order tells us that in the memory you take each and every row and put it inside the memory. You take each and every row and put it inside the memory. So what will it become? It becomes 0 0, it becomes 0 1, it becomes 0 2, and it comes as 0 3. Now you take the next row of your two-dimensional array and take it and put it in the next memory locations which are vacant. So just take 1 0, then 1 1, 1 2 and 1 3. Similarly, you take 2 0, 2 1, 2 2 and 2 3 and put it here. 2 0, 2 1, 2 2, 2 3. Sorry, I am running out of space, that's why I have written it like this 202122. And suppose our as we are using this, where as we are using this array where our starting index is 0, again we'll have to start with index 0, 0 1 2 3 4 5 6 7 8 9 10 and maybe 11. Okay, yes, 12 elements will be there. As we are using a 3 cross 4 array, there will be 12 elements. Now the obvious question that comes into our mind is that if we want to access some element, then what will be its address? We are concerned with the addresses. Okay, we are not concerned with each what is the index, because ultimately these index will have to be converted into physical address. That firstly into logical address, then logical address to physical address by our operating system. But we should know that what is the logic which is working behind this index and everything to convert it into logical addresses. Okay, now suppose I am interested in accessing this element 21. I want to find A21. Now see this, in order to go to this A21, we are considering here as row measure order. We'll start with the rows, the number of rows which we will have to cross. So in order to go to this 21 position, I will have to cross these two rows. First I will have to cross these two rows. So the number of row is given by 2, which can be supposed as I am having I cross j as the dimension. Then 2 is directly, we can write it as I. So it is, let me not generalize it. Let me first write what will be the address, and then we shall study that, then we will generalize it. Okay, suppose 2 into the number of columns we will have, because the elements present in each row, just focus here, what the number of elements present in each row is dependent upon the number of columns we have, isn't it? Because we have 2 rows and each and every row will have equal number of elements, which is equal to the number of columns we have, 1 2 3 4. So here it will be dependent upon the number of columns we have, so it is 4. So as we have seen that in order to reach this 21 element, we have crossed 2 rows. Each one is having 4 elements, exactly 4 elements. And how did we get this 4 element? By seeing the number of columns we have, because depending upon the number of columns we have, we will have the number of elements in each and every row. So once we reach, after crossing these 2 rows having 4 elements, we reach this position, and in order to reach to one position, we will have to cross one extra column. So we just write 1. Now as I told you that in memory each cell can have either 1 byte or it can have 1 word. So depending upon that, we will have to also see that how much size each and element is occupying in the memory. So suppose I am again in order to generalize it, I am just having size that can be, if it is byte addressable, that can be 1 byte or 2 byte, or if it is word addressable, that can be 1 word or 2 words. So we can write into size. Now again our starting address can be 100 or any other, starting address can be anything, that is called as the base address of our array in the memory. So we will have to add it with the with base address, we will add this entire. So by this we will get the exact memory location of A21. So we can solve it. 2 into 4 plus 1 into 1 plus 100. So what it will give is 4 into 2, that is 8 plus 1 9 plus 100, that is 109. So we can check here, if it is 100 then 101, 2, 3, 4, 5, 6, 7, 8, 9. 109, this element is at 109. So in this way we can easily find out that at which address location our element of the array is present. And let us now generalize it. We have seen that how we can easily derive the formula. Let us now just write the formula, and we shall see the next model then. Let me write the formula. So so here we are deriving the formula. Suppose I am having a ij. Suppose I am having m number of elements, m cross n, where n is the number of elements present in the column and m is the number of elements present in the row. So we can easily generalize it as I into, if I cross j is the dimension of the matrix, then we can write it as I into n plus j. Let me write it here. So I into n, that is, here you can see 2 into 4, okay, plus j, if it is my I and this is my j. So I, that is 2, n, that is the number of elements present, that is 4, the number of columns that we have, the number of columns we have, that is n, that is 4, plus j, this one is j, into size, whatever size it is. Previously I have considered that we are having one byte or one word of one word or one byte of cell. The size of each cell is 1 byte or 1 word into that size plus that base address. Previously we have considered that base address as 100. Okay, now the next thing that is important is I have considered that the elements will have a starting index of 0. Now, as I told you that it can be either 0 or it can be 1. So suppose I am having starting index, the element starting index, the element with starting index is 1. Then it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12, because we are having 3 cross 4 array. So in that case it is very easy, just you have to make some minor modification in the general formula. You just have to write it as I minus 1 into n plus j minus 1 into size plus the base address. So this is if my starting index is 0 and this is if my starting index is 1. So I hope that you got this point clearly, but we'll do more examples on this and the concept will be more clear now. As of now, if you don't understand anything, just go through it once again, and once we'll do some examples on it, these concepts will be more clear to you. Next we shall see how column major order works. Okay.